In this video I will show you in an experiment what happens when you connect two batteries to each other in series and what effects this has on the open circuit voltage and also on the internal resistance of this combined setup. I will also give you some theoretical background knowledge so you can really understand what's going on here and also make an informed prediction as to what the end result might be. And when we are finished with the experiment, we will check this prediction against the measurement results which we have taken to see if they both align. And as always, at the end there's going to be a summary of the most important facts for you. And my name is Andreas from The Fearless Engineer, and here we go. Now, before we start with the actual experiment, let's discuss some theoretical background knowledge which we need in order to understand what's going on here in the experiment. If you have watched the previous videos on voltage sources, you might know that there are several parameters which describe the behavior of a battery. For example, the internal resistance Ri, the open circuit voltage U0 or UO, and then the short circuit current Is. And the slope of the characteristic curve of the battery, this is determined by the value of the internal resistance. And the greater, the larger Ri, the steeper the slope of the curve. And here you can see two characteristic curves of two batteries, a blue one and a red one. And the intersection with these characteristic curves, the straight lines with the y-axis, is the open source voltage. And this means we have no current flow across the terminals. We directly measure at the terminals. We connect the measurement device to the open circuit, and this connection here is then not given, which means no current flow occurs. And this is the entire voltage drops across the measurement device. And this is why we can directly measure the open source voltage for a battery. And this is the intersection here. On the other side, once we short the terminals of the battery, we get the short circuit current, which means that the upper terminal, the positive terminal, is at the same potential than the negative terminal. This means a voltage drop of 0, which is why we can look at the intersection here on the x-axis. And for the first battery, the red one, the short circuit current is larger than for the second battery. And this means it can theoretically provide a much larger current flow, or seen in another way, for the same current flow, we get a smaller voltage drop for the blue battery than for the red battery. And this means a shallow slope, such as for the red curve here, is better than a steep slope, such as for this one here. And perfect would be a slope of 0, which means a line parallel to the I-axis. And when you compare the internal resistors, Ri and Ri2, or Ri1 and Ri2, this describes the slope of the curve, and a small internal resistance means a shallow slope, and a large internal resistance means a steep slope, which you can see here on this curve here. And a steep slope is worse than a shallow slope and a small slope. And these parameters can be described to identify the quality of a battery. Also, if you have seen the module on the Lemon battery, you might have seen that in the experiment, when we connect several Lemon batteries to each other, we could see an increase of the total voltage. So this is the setup which we have used in this experiment. Each of these components here denotes a single Lemon battery, and if you connect them in series, without going into much detail on how these batteries work, there's a video on that. What happens here is that we superimpose the electrical fields of each battery with each other. So if you have a flow of electrons here, which emanate, let's say, from the first battery, this flow progresses through the entire setup here, and with each new battery, the potential energy of the electrons is increased, and they add up. And this means that also the voltage drop increases with each new battery, simply because voltage drop is nothing but a difference in potential energies, and as the potential energy with each battery is increased, also the voltage drop needs to be increased. You can also argue this point by comparing the batteries to apples hanging from trees in the real world. If you observe an apple hanging from a first tree in a height of h1, then you can easily compute the potential energy of this apple at this height. If you have another apple, maybe another hanging on a tree which is slightly higher than the first one because it stands on a hill, let's say, and the height of the second apple is larger than the height of the first apple, you can also easily compute the potential energy of this apple, and it stands to reason that the potential energy of the second apple is higher than for the first one. And in an equation, this looks like this one here. The mass of the apple multiplied with the gravitational pull of the Earth, multiplied with the added up heights of the two trees or the two apples respectively. This gives you the potential energy of the apple hanging from the branch in the second tree. And in a circuit, you can do the exact same thing. You can compute the potential energy of an electron by multiplying charge of the electron, which corresponds to the mass, then the electric field, which corresponds to the gravitational pull, and the length, which means the distance from one of the battery terminals, which corresponds to the height. And the difference between these two examples is that in the case of the circuit, you do not add up the heights. This does not change for the electron, or at least not that much. What you do is here you add up the influences of the two electric fields, E1 and E2. So in the case of the circuit, you add up the electric fields. In the case of the apple, you add up the two heights. But in essence, basically, what happens here is the same. You increase the amount of potential energy. And if you look at this expression here in the gray box, we have seen this in another video on voltage drop. This corresponds to the voltage, the combined voltage of the two batteries. And you can easily see that adding up these electric fields here increases the overall voltage. And the expectation for such a series connection of batteries, as I mentioned before, arguing with the potential energy, is that also the internal resistances will add up according to the Kirchhoff loop theorem, which we talked about before. And if you look at it in a circuit, in a replacement circuit, you can see for the first battery that we have a perfect voltage source, U1, an internal resistance of the first battery, another perfect voltage source for the second battery, and also an internal resistance of this battery. And if you combine this in a loop equation, you get this one here, minus U1 plus UR1 minus U2 plus UR2 equals 0. And this can be reshaped to have the active components, the sources, on the left, and the passive components, the internal resistors, on the right. And you can see that the source voltages add up, and you can also see by using Ohm's law that the internal resistances add up because the current stays the same. This is our prediction on what's going to happen, and now let's find out in an experiment if this really is the case. The goal of this experiment is to measure the internal resistance of a series connection of batteries. We have done this before for a single battery, and we will first measure the internal resistance in this video now for this 9-volt block battery. Afterwards, we're going to do the same for another 9-volt block battery. This one is slightly aged, which is why I have marked it with this black strip here to be able to differentiate between the two very easily. And after we have measured the internal resistances of these two batteries here individually, we will connect them in series, perform the measurement again, and see how this new internal resistance of the series connection of the two differs from the individual resistances. That's the goal of this experiment. This setup here, which you can see, is the same which we have used previously. We have a 10 ohm resistor, and this resistor is connected to a multimeter, which you can see here, which is now switched off. Let's turn it on again. And as you can see here from the dial of the multimeter, it is set to current measurement. And after the current leaves the resistor, it enters this current meter here, leaves it again after performing the measurement, and leads back to the battery. This is the battery which will be connected to this black crocodile clip here on the left. And on the other side of the battery, we will connect another crocodile clip to the positive terminal of the battery, and from this terminal here the current flows back into the resistor. So we will perform a current measurement for a 10 ohm resistor using these two batteries here. Also, we need to measure the voltage drop across the resistor here in order to be able to compute the internal resistance, and this is something we can do by also measuring the voltage drop using these red crocodile clips, which lead to the left multimeter, which is set to voltage measurement. And just to give you an impression of the resistance value of this 10 ohm resistor, let's switch the dial to ohm. And you can see that the resistance of the resistor is 10.7 ohms, so there is a deviation to what's printed on the housing, but nonetheless we do not need, in our equations, we do not need the exact value of this resistor here. We need to measure current flow, we need to measure voltage drop, but we do not need this resistor value here. So just for curiosity, there is a small difference between what's printed on the housing and what the multimeter measures, but this is nothing which we will consider during our computations. Now let's perform the measurement with the first battery. Let's connect this connector here to the terminal so it's easier to attach them to the crocodile clips. Let's connect the negative terminal to the left crocodile clip and the positive terminal to the right crocodile clip. And in the displays of the multimeters you can see a voltage drop of 5.7 dropping 7.2, 7.1 volts, and you can see a current flow of 0.57 amps also dropping. The reason why we see this drop is that the resistor here is rather small, and this is quickly draining the charges from the battery. So we will later, when we compute the internal resistance, use a time-synced still frame from the video, and for now you can simply observe the rough magnitude of the voltage drop and the current flow for this first battery, which is the better one because I have not used it before in a circuit. Now let's perform the same measurement for the second battery. Let's put this aside and use the battery with a black marking, and also connect it to such a connector here. Let's connect the positive terminal to the left crocodile clip and the negative terminal to the right crocodile clip. And in the displays of the multimeters you can see slightly different values. The voltage drop now for the 10 ohm resistor is at 4.1 volts, also dropping, and the current flow is at 0.41 amps. So the values are lower than for the first battery, which already gives you a hint that this battery is not able to provide the same voltage as well as the same current flow as the first battery for the same load of a 10.7 ohm resistor. Now these are the first two measurements which we need to take. Secondly, what we need to do now is we need to measure the voltage drop for an empty load situation. In order to get these values, we now connect the crocodile clips of the voltmeter directly to the terminals of the battery, which I am doing just now. And in the display you can see a voltage drop of 7.28 volts, now increasing slightly because the charges are replenishing for the battery with a black marking. And now we can perform the same measurement of empty load voltage for the other battery. And as soon as I connect the crocodile clips, first this one, then the other one, to the multimeter as well, you can see a voltage drop which is higher. It's at 8.41 volts for the second battery. And now, in the next phase of the experiment, we will connect both batteries in series and then perform the same measurements again. And now we are looking at the series connection of the two batteries here. This little setup here, this blue thing, is called a breadboard. It's something which I already have made a video about. And let me briefly explain how the batteries are now connected. On the left side you can see the black crocodile clip, which leads directly to the multimeter to measure current flow as before. And this connector now is directly in series to the positive terminal of the left battery. Then after we leave the first battery through the black cable here, which is the negative terminal, we get into this row here, or column, in the breadboard again, and the negative terminal is now connected in series to the red terminal or to the positive terminal of the second battery. So we have minus and plus. And after we leave the second battery, we enter here in this column on the breadboard again, and the negative terminal of the second battery is connected in series to this white connector here. And as soon as I connect the crocodile clip, this one here, to the white connector, you can see a current flow and you can see a voltage drop. And this is the voltage drop of roughly 7 volts, 6.9, and quickly falling, same as the current flow, 0.68 amps, and also falling because the battery is now, both batteries are now discharging. And these values, they stem from the series connection of these two batteries here. And if you recall the values we have seen for each individual battery for this particular 10 ohm resistor here, you might note that both the voltage is higher and the current as well is higher. And before we can compute the internal resistance of this series connection of batteries, we have to measure the voltage without a load attached, and this is what we're going to do now. In order to measure this value, I simply connect the crocodile clips of the voltmeter directly to the white connectors here. And the voltage drop, which you can see on the left multimeter, shows a voltage of 15.2, 0.3, 0.4. It's increasing now because the charges are replenishing. Roughly 15.5 volts of voltage drop if no load is attached for this double battery setup here. And now we have all the values in place which we need in order to measure the internal, or to compute the internal resistance of these two 9-volt batteries which we just have connected in series. Now let's take a look at our measurement results and at the evaluation which we can perform using these results. We have the formula for computing the internal resistance here, which we have derived in the previous video. Also, you can see the measurement results here, the open load circuit, the open load voltage drop, also the operating point for connecting this 10 ohm resistor here. And if I enter these values into the equation here, open load voltage minus minus voltage for the operating point divided by the current flow for the operating point, we get an internal resistance of roughly 9 ohms, 8.98 ohms for this first battery here. And for the second battery, we're going to do the same. The open load voltage here is at 8.6 volts and the operating point is slightly higher, 5.9 volts and 0.593 amps. And if you enter these values here, you will find a significant difference with regard to the internal resistance of the second battery. This is only at 4.55 ohms, so significantly smaller than for the first battery. And now let's get to the series connection. We can conduct individual measurements and we can then apply the predictions which we have made in the theory introduction to this video. Adding up the internal resistances leads us to a prediction of 13.53 ohms for the expected internal resistance of the combined battery when we connect it in series, the two individual ones. And also the individual voltage drops can be added up to the combined voltage drop of 16.42 volts. If we conduct the actual measurement for this series connection, we get an open circuit voltage of 15.45 volts and also an operating point of 7 volts and 0.706 amps. And if I enter these values into our formulas, we get an internal resistance of 11.97 ohms, so roughly 12 ohms, which is not that far away from our prediction. And given the inaccuracies of the setup here and also the individual resistances of the measurement leads leading to this setup here, there's some deviation to be expected. So what we get here is a value which is in the ballpark of our expectation, and we can say that we have now successfully verified the prediction which we made when we set out using the equations. The same holds true for the open circuit voltage drop, which is roughly in the ballpark of our prediction. There's a 1 volt difference, but nonetheless roughly what has been expected, namely that the two individual voltages would add up, has been verified in the experiment. So if you want to increase voltage drop, combine two batteries in series, but this also increases the internal resistance as we have seen now. Now let's get to the summary of the most important takeaways from this experiment here. We have seen that the internal resistance of a 9-volt battery is much higher than the internal resistance of, let's say, a 1.2 volt rechargeable battery, as in the previous video. And the internal resistance increases when the battery charge is depleted. This is something which we have seen because we have looked at two batteries, one a bit older and half depleted, and the other one taken freshly from the box, and there has been a significant difference in terms of the internal resistance of the two. Also, when batteries are connected in series, the open circuit voltages and also the internal resistance values, they add up. The values of the individual batteries add up to a combined value. So in conclusion, we can say that if a higher voltage is required, batteries can be connected in series. Also, you need to take into account that the quality of the voltage source decreases with each new battery which is added to the circuit. And if you, for example, take a 9-volt battery, this already is a series connection without you maybe knowing it, because inside the housing of the 9-volt battery there are 6 1.5 batteries which are connected in series to each other. And this also explains the first point here, where we saw that the internal resistance of the 9-volt battery is higher than for the 1.2 rechargeable, and this is simply because we have 6 individual internal resistances already added up in the 9-volt battery. That's all for this video here. If you have any questions, please drop me a comment down below. And now this is all from me. I wish you a nice day. See you next time here on The Fearless Engineer.